Hello again, Math 30-1. We're looking at rational graphs today when they're not in the transformed form. So for example, if you look at A here, it's y equals x minus 3 over x plus 4. There's an x in the numerator, so it's not in transformed form. So we can't just give our asymptotes from our vertical and horizontal translations. So that's what we're going to do today. So steps to determining the vertical asymptote. To determine the non-permissible values, NPVs of the rational equation. Note, if there's a factor that cancels off in the numerator, the top, and the denominator, the bottom, it is a point of discontinuity, not a vertical asymptote. So, example, determine the vertical asymptote of the rational equation. So if I look at the top, it's x minus 3, technically in brackets. And the denominator is x plus 4. So nothing cancels off. So what we have to do is we have to find the non-permissible values for the denominator. So what would make the denominator be 0? And we did this in grade 11. So we're going to say the non-permissible values. And where that value doesn't exist is actually where the vertical asymptote does exist, because that's where the graph is not. Okay? So if we go x plus 4 cannot equal 0. And then I move my 4 over, so I subtract 4. I get x cannot equal negative 4. So where's my vertical asymptote at? There, because the asymptote's where the graph doesn't exist. So I have a vertical asymptote at x equals negative 4. And it's as easy as that. Okay? For B, I have 2x plus 1. And on the denominator, I have 3x minus 2. All right? I'll show it with graphing calculators after when we connect also the horizontal asymptotes, but for now we're just going to find them algebraically. So the numerator and the denominator don't have a factor that cancel because they are separate factors, 2x plus 1 and 3x minus 2. So I just find the non-permissible value for 3x minus 2. So I say 3x minus 2 cannot equal 0. Solve. Add my 2 over. 3x cannot equal 2. And then I divide by 3. X cannot equal 2/3. So if I plug 2/3 into the denominator, I would get 3 times 2/3, which is actually positive 2. 2 minus 2 is 0. So I know I'm right. I can check it by plugging that value back into the denominator and seeing if it equals 0. So x cannot equal 2/3. So for this question, I have a vertical asymptote. Because remember, the vertical asymptotes are always the x equals ones, because it cuts through the x-axis. A vertical asymptote at x equals 2/3, because the asymptote is where the graph doesn't exist. For C, I have a 3 on the top and then a quadratic on the bottom. So when I have a quadratic on the bottom, the first thing I need to do is actually factor it. So I have to do decomposition. So 2x squared minus 7x minus 4. So I ask myself, what times what equals the outside numbers, so 2 times negative 4. So what times what equals negative 8, and what plus what equals the middle number, negative 7. So it's going to be negative 8 and positive 1. Negative 8 times positive 1 is negative 8. Negative 8 plus 1 is negative 7. So I get 2x squared minus 8x plus 1x minus 4. I replace that middle term with it. And I group. I can take a 2x out. Of 2x squared minus 8x, I'm left with x minus 4. X minus 4, I can take a plus 1 out, I'm left with x minus 4. And then the GCF I can take out of the two terms is x minus 4. And then what's left over is 2x plus 1. So this equation is actually the same as 3 over x minus 4, 2x plus 1. So I'm going to get 2 non-permissible values. So I'm going to get 2 asymptotes, vertical asymptotes. And the reason why I get 2 is because nothing cancels off. So I'm for sure not getting, if nothing cancels off, I'm not getting a point of discontinuity. They're both asymptotes. So I'm going to go x minus 4 cannot equal 0, and 2x plus 1 cannot equal 0, separately. And I'm going to go x minus 4 cannot equal 0. I'm going to add the 4 over. So I get x cannot equal 4. And then 2x minus 1, I'm going to subtract the 1 over. So I get 2x cannot equal negative 1. And then I'm going to divide by 2 to get x by itself. So x cannot equal negative 1/2. So I have two vertical asymptotes because the graph doesn't exist in two places on the x, the 4 and at negative a half. So I have vertical asymptotes at x equals 4 and negative a half. Okay, so vertical asymptotes are easy. It's just the non-permissible values, as long as it doesn't cancel on the top and the bottom. The horizontal asymptotes, the y equals asymptotes, follow rules. Okay? So these are the rules. Rules for determining horizontal asymptotes and or points of discontinuity, because you could have both or have just one or the other. If the numerator degree is less than the denominator degree, the horizontal asymptote will always be y equals 0. Always y equals 0, because when the numerator is a smaller degree than the denominator, the equation has no vertical translation. So the equation of the vertical asymptote does not change from the parent function. So technically, if I have 3 over x plus 4, I would technically have a plus 0 at the back. So it's not vertically translating anywhere. So my y equals 0 would stay y equals 0. So how can we check? The degree of the numerator is x to the 0, technically. If there's no x, it's x to the 0. The degree of the denominator is degree 1. So the degree numerator is 0, degree denominator is 1. So if the degree of the numerator is smaller than the degree of the denominator, we have a horizontal asymptote at y equals 0. Remember, the horizontal asymptotes are always y equals. Let's find the vertical just because we can. So we have x plus 4 in the denominator. It doesn't cancel one of those x plus 4s in the numerator because there isn't one. So I just go x plus 4 cannot equal 0. X cannot equal negative 4 by moving it over. So I have a vertical asymptote as well. At x equals negative 4. Now let's look at this graph. So I'm saying I have a vertical asymptote up and down at x equals negative 4 and a horizontal at y equals 0. So I can check these by looking at it. I can get my calculator to show. 1 second. Okay, so I go to my calculator and I type in the equation that I had. So alpha y equals enter, if you have that button. So you're going to go 3 over x plus 4. If you don't have that button, you're going to have to put the numerator in brackets divided by the denominator in brackets. So bracket 3, close bracket, that's my numerator, divided by bracket x plus 4. Okay? So if you don't have the alpha y equals button, you have to put your numerator in brackets and your denominator in brackets, or it's not going to work. Now the blue will draw and the red will draw on top of it to prove that it works either way you type it in. Blue, red. Now I said we had a vertical asymptote at negative 4. So there's this dashed vertical asymptote at negative 4, which there is. It's for the graph can't exist, so my asymptote is there. And then I have a horizontal asymptote at y equals 0. And even though this red looks like it's getting really close to 0, possibly on it, if you went to your table of values, and I go to larger, I'm actually just getting decimals. Okay? So if you type in the original way I typed it in, you're going to get fraction y equals. If you type it in with the brackets, you get nice decimals. So you can see, the larger I get in my x, I'm still not getting to 0. I'm getting closer and closer, but I'm still not getting there. Okay? So proving what we did was correct. Okay. For this one, we have y equals negative 2 over, we can factor our denominator. What times what gets me negative 2? What plus what gets me negative 1? Negative 2, positive 1. And we can go right to brackets because there's a plus 1 in front of this x squared. So x minus 2, x plus 1. Now my numerator is degree 0. Because it's x to the 0 if there's no x. And this one's degree 2. So my numerator is still smaller degree than my denominator. The moment that happens, I have a horizontal asymptote at y equals 0. Don't even have to look for anything. It's immediately that. Now I have two non-permissible values that don't cancel. So I have x minus 2 cannot equal 0, and x plus 1 cannot equal 0. So x cannot equal 2 when you add that 2 over. X cannot equal negative 1 when you add that over. So I have vertical asymptotes. Graph doesn't exist at those, so I have vertical asymptotes at x equals 2, comma, negative 1. Type this one in just to show you again. So I would go alpha y equals enter, negative 2 over x squared minus 1x minus 2. Or if I don't have that button, I'm going to go bracket negative 2 divided by numerator in brackets, denominator in brackets. X squared minus 1x minus 2, close bracket. And I'll get the same graph. Okay, I said I have a vertical asymptote at x equals negative 1 and 2. Look at that. And I have a horizontal asymptote at y equals 0. So we can check these and see if what we're doing looks legitimate. Okay? We don't ever want to do these based off of guessing if the graph is correct and then just guessing what they are from there, because we'll get fractional ones and you're not going to get those right. So you have to do it algebraically. You have to do it using the rules, but you can always look at your calculator and check it. All right. What happens if the numerator degree equals the denominator degree? Well, if that happens, the horizontal asymptote will always be a fraction of the leading coefficients of the numerator and the denominator. Okay? So this is degree 1, degree 1. So my horizontal asymptote is going to be those coefficients in front of those degrees. So it's going to be y equals negative 3 over 2. Now, the way they can trick you is they can write it out of order. So they could go like 2 minus 3x over 2x plus 1. Either way, these are degree 1, and the leading coefficients are the numbers in front of the largest exponent. So either way, this would still be negative 3 over 2. So don't let it fool you. It's not always just the first number. It's the leading coefficient. So it's the number in front of the largest variable. So either way, if they even rewrite it out of order, it still would be y equals negative 3 over 2. So that's my horizontal asymptote. And then I have 2x plus 1 cannot equal 0. 2x cannot equal negative 1 by subtracting 1 over. Divide by 2. X cannot equal negative 1/2. So I have a vertical asymptote at x equals negative 1/2. So we'll type that one in. So I go to my y equals, I clear them out, and now I'm going to type in alpha y equals, enter, negative 3x plus 2 over 2x plus 1. Or if I don't have that button, I do numerator in brackets divided by denominator in brackets. And I will get the same graph. Okay, so we said we had a horizontal asymptote at negative 3 over 2. That's negative 1.5. There's no way you're guessing that. So if you don't actually know the rules, you're going to probably guess negative 1 or negative 2 as your asymptote, and that's wrong. So we need to know our rules, okay? And then we said that we had it at negative 1/2, x equals negative 1/2. So I go to x equals negative 1/2, which is right here. So I was going to my x-axis to that value and then follow it down. Good chance you're probably not picking negative 1/2, you're probably picking 0 or 1. So it is always good And important to know how to do it correctly, not just try and look off your graph. Okay? The next one, degree 1, degree 1. So this one's going to be the numbers in front of those, so 3 over 1. Like, once again, they could be rearranged, but you always take the number that's the leading coefficient. So I have a horizontal asymptote at y equals 3 over 1, which is just the same as saying 3. Okay? And then I go x minus 1 cannot equal 0, add the 1 over. X cannot equal 1, so I have a vertical asymptote. At x equals 1. Points of discontinuity. So what happens if, when we factor, the factors cancel in the numerator and denominator? Well, then you're going to get a point of discontinuity. So if I factor the top, it's what times what gets me 6, and what plus what gets me negative 5. So it's going to be x minus 2, x minus 3. They both need to be minus. You can't pick 6 and 1. Some people want to pick negative 6 and positive 1. Well, that won't get you positive 6. Remember, we need what times what equals 6, what plus what equals negative 5. So it needs to be both negatives. So you can't use negative 6 and 1, because that will get you negative 6, not positive 6. On the bottom, we get x minus 3. The moment the two factors cancel off, that's going to be an open dot on your graph, a point of discontinuity. Okay? So x minus 3's, they cancel. So I have x minus 3 cannot equal 0. So I add my 3. So x cannot equal 3. This is true. But this is no longer a vertical asymptote. Because it cancels on both the top and the bottom, it's actually a point of discontinuity. So you have a point of discontinuity. If it didn't cancel, it would be a vertical asymptote, because it canceled discontinu. It tried reading and writing at the same time, did not work. So point of discontinuity. So it's going to be at 3 and something. We need a something because it's a point of discontinuity. We need a y. How do we find the y of a point of discontinuity? I'm going to write it over here. To determine the y value of the point of discontinuity, you substitute or plug in your x value into the reduced y equals equation. So my reduced y equals equation technically is this. It's y equals x minus 2 because these canceled off, right? So now I'm going to go y equals x minus 2, take the reduced equation and plug the 3 in for x. So I'm going to get y equals 3 minus 2, y equals 1. So I have an open dot at 3, 1. Okay? So I have an equation y equals x minus 2. All I have left is x minus 2. So I have no vertical asymptotes. There's nothing left in the denominator after I take that point of discontinuity off. So if I have no vertical asymptotes, I don't have a horizontal. Okay? You cannot have a horizontal if you don't have a vertical. So technically, all I have is the line x minus 2 with an open dot at 3, 1. Okay? We'll type it in so you can see. So we'll do the same 2 ways again. So I'm going to go alpha y equals enter. On the top, I have x squared minus 5x plus 6. And on the bottom, I have x minus 3. Or numerator, x squared minus 5x plus 6. Ooh, I have two plus signs up here. That would have not been good. And two minus signs. All right. Bracket divided by bracket x minus 3. This graph. And I have a straight line. What the heck? Well, once those canceled off, I had just a straight line at y equals x minus 2, which I have. Now you might say, well, there's no open dot. There actually is. The graphing calculators, a lot of them want to have continuous functions, so they'll force it to look like it's not open, but it is. So if I go second graph and I go to, I need my table, come on, and I go to 3, look, there is no y. There's an error. Okay? So what did we say? Well, we said at 3 and 1, there's an open dot. So actually on this graph, at 3 and 1, would have an open drawn dot like this. This red would not exist. It would just be a line like this if you drew it to an open dot at 3, 1, which is called the point of discontinuity, and then it would keep going. So the graph still doesn't exist at x equals 3, and it still doesn't exist at y equals 1, but it's called the point of discontinuity, not asymptotes. All right, let's go to the other one. So if I factor this one, what multiplies to give me 9 and adds to give me negative 6, I'm going to get x minus 3, x minus 3. And I can go right to brackets because I have a plus 1 in front. The denominator, x squared minus 9, is the difference of squares. So when you square root the x squared, you get an x. When you square root the 9, you get a 3. And then it's a difference of squares because it has to have a minus sign. If it has a plus sign, there's nothing you can do about it. With a minus sign, one of these is minus and one of them is plus. So, oh, x minus 3's cancel. They cancel again. So I'm going to end up with an equation, f of x equals x minus 3, x plus 3. Okay, that's going to be my end equation. All right, I have a point of discontinuity because a factor canceled. So when x minus 3 cannot equal 0, x cannot equal 3. So I know I have a point of discontinuity at 3 and a y value because it's a point of discontinuity. How do I get the y value? Well, I plug it into the reduced. So it says the y value of the point of discontinuity, you substitute your x value into the reduced y equals equation. So I'm going to substitute 3 into the reduced equation. So I'm going to get y equals 3 minus 3 over 3 plus 3, which is 0 over 6, which is 0. So my coordinate, my point of discontinuity is at 3 and 0. Those are not asymptotes. And I know that the horizontal or the vertical asymptote normally would be what the NPVs are. But remember, if it cancels off, it's a point of discontinuity. Now, unlike the previous equation where it was just y equals x plus 2, this one actually has a rational left behind. X minus 3, x plus 3. So I can have a point of discontinuity and asymptotes, which I do. Look, I still have this x plus 3 in the denominator. I still have a non-permissible value. So x plus 3 cannot equal 0. X cannot equal negative 3. That's a vertical asymptote because it didn't cancel. If it cancels, it's a point of discontinuity. If it doesn't cancel, it's a vertical asymptote. So I have a vertical asymptote because I still have a factor in the bottom that didn't cancel off at x equals negative 3. And the moment I have a vertical asymptote, I have a horizontal as well. Well, let's look. Horizontal follows the rules. Is the degree of the numerator smaller than the denominator? No. The degree of the numerator is the same size as the degree of the denominator. So I take the fraction of their coefficients, 1 and 1. So I have a horizontal asymptote at 1 over 1. At y equals 1 over 1, which is just y equals 1. Okay? So not only do I have a point of discontinuity, and I have a vertical and horizontal asymptote. Let's see what this looks like. So we're going to go alpha y equals, enter, x squared minus 6x plus 9 over x squared minus 9. Or you could do numerator in brackets divided by denominator in brackets. Okay, so we said we have a horizontal asymptote at 1. So I'm going to go to y equals 1 and then follow it along. Looks like we're right, y equals 1. We said we have a horizontal asymptote at -3, x equals -3, so I'm going to go to where x equals -3, draw a dashed line, and then carry it up. That looks right. And then we said we have a point of discontinuity at 3 and 1. So there should be at 3, not 3 and 1, 3 and 0, sorry, I was looking at the previous equation. 3 and 0, there should be an open dot here. This shouldn't exist. There should be an open dot here. Well, let's check. Second table. Yep, 3, an error. There isn't a graph there. So we do have an open dot. So you have to remember to look for that point of discontinuity because your calculator's graph is not going to show it to you. It's not that nice. It'll show it to you if you look for it, but it doesn't immediately, you don't immediately see it. Okay, next page. So discuss each non-permissible value in the graph of the rational function. So it's the graph of the rational function over here. We're going to factor. So we're going to say what times what gets me 6, what plus what gets me 5. It's going to be x plus 2, x plus 3. In the denominator, we're going to say what times what gets me -21, what plus what gets me -4, x minus 7, x plus 3. Wait a second, the x plus 3's cancel. The moment they cancel, I have a point of discontinuity. So I'm going to go x plus 3 cannot equal 0, x cannot equal -3. Okay, my reduced form of my equation now is y equals x plus 2 over x minus 7. To get my y value of my point of discontinuity, I plug -3 into that. So I'm going to go y, that does not look like a y equals -3 plus 2 over -3 minus 7, which is -1 over -10, which is 1 over 10. So I have a point of discontinuity at -3 and 1 over 10. So at -3 and 1 over 10, there should be an open dot here. That's a mistake on the graph. Okay? Then I have this left over. This left over gets me an NPV is still in the denominator. X minus 7 still cannot equal 0. X cannot equal 7. Well, because it didn't cancel off, that's not a point of discontinuity. That's a vertical asymptote. So I have a vertical asymptote at x equals 7. Then I use my rules. The degree of the numerator is the same as the degree of the denominator, so I take a fraction of their leading coefficients. So my horizontal asymptote is at y equals 1. Okay? Algebraically determine the x-intercept. So if we take the factored form, we're going to get x plus 2, x plus 3, x minus 7, x plus 3. I made y equals 0 because the moment I see x-intercept, I immediately have to make my y equals 0 in my equation. That's how you find your x-intercept. Now these canceled. So I'm left with 0 equals x plus 2 over x minus 7. Now I can get rid of this x minus 7 by multiplying by it, both sides. What's 0 times anything? So 0. So 0 times x minus 7 is still 0. So now I have 0 equals x plus 2. And then I just subtract 2. So I get x equals -2. So I have an x-intercept at -2 and 0. So this factor that remains on the top after you've canceled off your points of discontinuity, that factor is actually, if you solve it out, your x-intercept always. Isn't that cool? Okay, you're going to try this example. and then you'll play it when you're done it. So for the rational function y equals x plus 2 over x squared plus 3x plus 2, determine whether the graph of the function has an asymptote or a point of discontinuity, or both technically. Determine the equation of the asymptotes and or the points of discontinuity. So the first thing we have to do is factor. We get x plus 2 on the bottom. We get what times what gets me 2, what plus what gets me 3. It's going to be 2 and 1, and because there's a 1 in front, I can just go right to brackets. So x plus 2, x plus 1. These they cancel. The moment they cancel, you still have a 1 up here. Don't put a 0, please. You have a 1 up here. So I have 1 over x plus 1 as my reduced form. The moment they cancel, I know I have a point of discontinuity. So I have a point of discontinuity. So I do x plus 2 cannot equal 0. X cannot equal negative 2. So I have this point of discontinuity at negative 2 and something. How do I find that something? I plug it into my reduced form. So my reduced form is y equals 1 over x plus 1. And now I'm going to plug negative 2 in for x. So 1 over negative 2 plus 1. So it's 1 over negative 1. So it's at negative 1. So I have a point of discontinuity at negative 2 and negative 1. Okay? Now this is left over. It's not just a line that's left over. I actually have a rational left over. The moment I have a rational left over after I cancel, I have a vertical asymptote and a horizontal. Okay? So if there's not just a line left over, like it's just a factor like x plus 2, but still a rational, you're going to get a vertical and a horizontal asymptote. So my vertical asymptote is my MPV. I have a vertical asymptote at, let's figure it out, x plus 1 cannot equal 0, x cannot equal negative 1 by moving it over. So I have a vertical asymptote at x equals negative 1. Horizontal asymptotes happen if I have a vertical. So if I have a vertical, I know I have a horizontal. What do? I look at my degrees. So this one is degree 0, technically, and this is degree 1. The numerator is a smaller degree than the denominator. That is when you should do like cartwheels in your house or something, because y equals 0 then. When your numerator is a smaller degree than your denominator, no work, not even a fraction, nothing. You just y equals 0, okay? So I have a point of discontinuity at negative 2 and negative 1. I have a vertical asymptote at x equals negative 1 and a horizontal asymptote at y equals 0. Here's another one for you to try. So you'll try it. You'll pause me, and then you'll come back and check it out. So if I factor this top, I'm going to get what multiplies to give me negative 14 and adds to give me 5. So it's going to be x plus 7, x minus 2. And I can go right to brackets because there's a 1 in front. I don't have to do decomposition. Now the bottom, what multiplies to give me negative 21 and adds to give me 4. So x plus 7, x minus 3. Once again, I can go right to brackets because there's a plus 1 in front. What the heck? Factors are canceling. The moment a factor cancels, I have a point of discontinuity. So I'm going to do this here. Point of discontinuity at, okay, x plus 7 canceled off. So I'm going to go x plus 7 cannot equal 0, minus 7, minus 7. X cannot equal negative 7. So I know I have a not equal to point at negative 7. Okay? And if you notice, that factor's on the top and the bottom, right? The x minus 2 is my x-intercept, and the x minus 3 gets me my vertical asymptote, right? So all of these things in this equation here make sense. The x plus 7 is the factor of the point of discontinuity. The x minus 2 is the factor of the x-intercept. And the x minus 3 is the factor of the vertical asymptote, which is going to come in handy in a little bit. Okay, so I have x equals negative 7. My reduced form of my equation is y equals x minus 2 over x minus 3. I use that to get the y of my point of discontinuity. So I'm going to go y equals negative 7 minus 2 over negative 7 minus 3, which equals negative 9 over negative 10, which is 9 over 10. There's no way you're getting that number unless you know how to do the math. There's no way you're guessing 9 over 10 as the y value of that point of discontinuity. Okay? Now, what's left over after I cancel? A rational. The moment there's a rational left after you cancel, you have vertical and horizontal asymptotes. So I have x minus 3 cannot equal 0. X cannot equal 3. So I have a vertical asymptote at x equals 3. Now for horizontal, I look at my degrees. Degree 1, degree 1. They're both the same degree. So I take the numbers in front and make a fraction of it. So it's going to be 1 over 1. So it's going to be y equals 1. Is going to be my horizontal asymptote. Now, where these asymptotes and point of discontinuity actually exist is where the graph does not exist. So those are the non-permissible values. So where these points of discontinuity and asymptotes exist is where the graph actually does not exist. So for non-permissible values, my x values that don't exist are the x of the point of discontinuity, x does not equal -7, and the x of my asymptote. So x does not equal 3, and I can just put a comma instead of writing them out separately. Where do my y's not exist? Well, the y of the point of discontinuity and the y at the horizontal asymptote. So the y of the point of discontinuity is 9/10. So that doesn't exist on this graph. It's going to be an open dot. And y equals 1 is where the horizontal asymptote exists. So that's where the graph doesn't exist as well. So once you've found your points of discontinuity and your asymptotes, you actually have the non-permissible values. Okay? Features exhibited at each non-permissible value, we've already written it. We have a point of discontinuity, we have a vertical and horizontal asymptote. So that is answered down here. Okay? Easiest way to do your domain. Remember where your asymptotes exist, you would just say x can't equal that, and then you'd have XER. And for your range, you just have where your asymptote and point of discontinuity exist. Say it can't equal that, YER. Okay? So once you've found your point of discontinuity and your asymptotes, you actually have your domain and range. And you would laugh at me teaching right now because I'm literally walking around the room pretending I'm talking to people. I just realized I have been wandering. Okay, so if you don't think we miss you guys, we 100% do. All right, the domain. X can't equal 3 or -7. So that's the first thing we're going to state. So we're going to go domain. Squiggly brackets means such that, the set of values, the set of values. And the variable we're using is x in here for all the domains, such that, straight up and down line, x cannot equal. What are the two things x can't equal? X can't equal -7 because that's the x of the point of discontinuity. And x can't equal 3 because that's my vertical asymptote. But x can equal everything else. So we follow behind with but, which is the little squiggle, or as well, x is an element of the reals. So what does that mean? That means x is every value but -7 and 3. That's the easiest way to write it. Could you say x is less than -7, x is between -7 and 3, x is greater than 3? Sure, you could. That is a long-winded way of writing your domain. The fastest way is just saying it can't equal -7 and 3, but it can equal everything else. That's the XER part. Okay? Range. Where do people err? They only put the horizontal asymptote, and you guys forget the y of the point of discontinuity. Always. When I mark these, always. The horizontal asymptote will be written, but you guys will forget the vertical, the y value of the point of discontinuity every time. It's just sad marking it. So we're not going to do that anymore. We're going to remember it. So we're going to go y cannot equal the y of the point of discontinuity because that point doesn't exist. So 9/10. And y does not equal the horizontal asymptote, which is 1. But y is every other real number. Okay? All right. Next one. Without using technology, match these. Okay, well, let's factor. Y equals x plus 4 on the top. What multiplies can be -4 and adds can be -3. X minus 4, x plus 1. Does anything cancel? No. Don't go back and be like, oh, it must cancel. It doesn't have to. If nothing cancels, then we just end up with 2 vertical asymptotes. So we have 2 of them because it didn't cancel. X plus 4 and x minus 4 are not the same. X minus 4 cannot equal 0. X plus 1 cannot equal 0. So x cannot equal 4. When I move that 4 over, x cannot equal -1. So I actually have 2 vertical asymptotes. they're at x equals -1 and 4. And if I have a vertical asymptote, I have a horizontal asymptote. They go hand in hand. So horizontal uses my rules. What's my rules? The degree. The degree of the numerator is x to the 1. The degree of the denominator is x squared. The numerator is smaller than the denominator. So I have a horizontal asymptote at y equals 0. Well, let's look here. Horizontal asymptote at y equals 0. Two vertical asymptotes. One's at -1. One's at 4. So this matches graph C. Let's look at B. We get y equals x plus 4 over, what multiplies to give me 4 and adds to give me 5? X plus 4, x minus 1. Factors cancel. Don't forget that when you cross off factors, these are actually 1s. So you're left with a 1 on the top, not a 0. Please don't put a 0. So our reduced form is 1 over x minus 1. So I have a point of discontinuity. It canceled. What's it at? Well, it's at -4, because that's what canceled. X plus 4 canceled, so it's at -4. How do I find my y? Well, I plug it into my reduced form. So y is going to equal 1 over -4 minus 1. So 1 over -5. Or -1 over 5. So at 4 and -1/5, I have a point of discontinuity. I still have a rational left over. If I have a rational left over, I have asymptotes. So I have a vertical asymptote where? Well, I go x minus 1 cannot equal 0. It's the factor that's left over. X cannot equal 1. So at x equals 1, I have an asymptote. The numerator of the canceled form is x to the 0 over x to the 1. So the numerator is smaller than the denominator. So I have a horizontal asymptote at y, not x, y equals 0, because the numerator is smaller than the denominator. So y equals 0 is actually the x-axis. X equals, oh, this is a positive one. This is x minus 4, or x plus 4, x plus 1, sorry. This is x plus 1. Oh my goodness, mistake, mistake. So this is going to be an x plus 1 that I'm going to fill it into. Sorry. So I'm going to get 1 over -4 plus 1. So it actually ends up being -1 over 3. See, and I caught myself because I looked at the equation, and here there's an asymptote at -1, not positive 1. So when I looked here, oh, it is supposed to be x plus 1. So this is x plus 1 up here. So then this would actually be x plus 1 cannot equal 0, which would make this be -1, which would make this be -1. And then my graph is actually right. So you can catch yourself, right? If you graph it after and look at it. And then at -4 and -1/3, I have an open dot. So this one is B. And then all you will go, okay, the last one's A then. You do that all the time, but we have to show why it's A. So if we factor the top, we can just take a GCF of x out. That's all we can do. So we take an x out, and we're left with x plus 4. Bottom is x plus 4. They cancel. So I'm just left with y equals x. I'm not left with a rational. So this is one of those where you're going to get a line with just a point of discontinuity and no asymptotes, because this is y equals x. It's just a line. It's not a rational after we've canceled. So we have point of discontinuity, and that's it in a line. So you have point of discontinuity at x plus 4 cannot equal 0, x cannot equal -4. So we know we're at -4 and something. So we go y equals x, plug it into that, y equals -4. Well, our point of discontinuity is at -4, -4. When I draw the line y equals x. Well, here's the line y equals x. We know that. It's the identity line. It's 1, 1, 2, 2, 3, 3. So we draw that line. But at -4, -4, we have an open dot. So it is A. I know this lesson is long, but it's a complicated one. I'm sorry. So the last thing we're going to do is write equations of graphs, okay? When you go to write an equation of a graph, you will always do this. You will always go y equals a x-intercept factor. This doesn't mean the actual x-intercept. Use the x-intercept to get the factor. The P of D, the point of discontinuity on the top. Point of discontinuity on the bottom, because remember, they're on both the top and the bottom, and they would cancel. And your vertical asymptote. Okay, when we go to do an equation, whenever there's a point of discontinuity, we have to use this form. All right, so we need three things. We need our x-intercept. Our x-intercept on this graph, these are going up by 2's, or down by 2's in this case. We have an x-intercept at x equals -2. Now we need to work it back to get the factor, because we only put factors into the equation. So how do I work it back? I get it to equal 0. I'm going to add the 2 over now. I work it back. So I get x plus 2 equals 0. Okay? So I'm going to get y equals a. I don't know what that is. My x-intercept is x plus 2, the factor of it. Okay? Now I need the point of discontinuity x. And work it backwards. The point of discontinuity x is at in between 2 and 4, so it's at 3. So I have a P of D. Please don't write P of D. I'm just writing it because I can right now. But on a test you would write, or on your assignment, you're going to write point of discontinuity. Okay? So our point of discontinuity is at x equals 3. Now we need the factor of it. So we're going to work it back. -3, -3. X minus 3 equals 0. So in the point of discontinuity spots on the top and the bottom, I'm going to get x minus 3, x minus 3. So the last thing I need is the vertical asymptote. Do I have a vertical asymptote? No. If I don't have a vertical asymptote, I will fill nothing in for that. So there's my equation. The only catch with your equation is you need to take a point and solve for that a value, because there could be a stretch factor, or there could be a reflection in the x-axis, which would cause it to be in different spots, okay? So we are going to solve for that a by using this as my x and my y. Now, to solve for the a, you're going to go y equals a x plus 2, x minus 3 over x minus 3. You're going to fill in for x and y. So we're going to get -2 equals a, -4 plus 2, -4 minus 3, -4 minus 3. So we get -2 equals a times -2 times -7 over -7. Now before you go to solve, the first thing you need to do is cancel these -7's off. So now I have -2 equals -2a, divide by -2. A actually equals 1. It doesn't always equal 1, but in this case it equaled 1. So there's no stretch and there's no reflection. So my equation is going to be 1, x plus 2, x minus 3 over x minus 3. And often they will FOIL factors. So we're going to get x squared minus 3x plus 2x minus 6 over x minus 3. And so my equation is going to be y equals x squared minus x minus 6 all over x minus 3. You could try B on your own. I'm going to skip it for now. But the way you can try it is you can make your equation, you can type your equation into y equals and see if you actually get graph B. Okay? Flipping over. So, we're going to go to D. This is taking a while longer, so we're going to skip C, okay? We're going to go to D. D is not just a line this time, so we're actually going to have a vertical asymptote. So remember, in order to get our equation, we're always going to go y equals a x-intercept, point of discontinuity. What if there isn't a point of discontinuity? Well, then we would leave those brackets off, right? Just like we left the vertical asymptote one off. vertical asymptote, and then P of D. So we need all those pieces in order to fill it in. Okay? So, do our X-intercept first. We have an X-intercept at X equals, and we only care about the X values of these, X equals 7. So when I work that back, to get it to equal to 0, I'm going to subtract 7. So my factor is X minus 7 equals 0. So in for X-intercept, I'm going to have X minus 7. Okay? Point of discontinuity, I just need the X value of it. The X value of the point of discontinuity is at -3. So I have a P of D, point of discontinuity, X equals -3. So when I'm filling in the equation, I'm literally just filling in the X values to get the equation. So I'm going to add 3 over, and I'm going to get X plus 3 equals 0. So that's going to go for my point of discontinuity on the top and on the bottom. This time I actually have a vertical asymptote. My vertical asymptote, and I don't care about my horizontal when I'm making the equation, because when I'm making the equation, it'll cover for my horizontal for me. And that's why my A is useful, because it also will make my horizontal asymptote correct if it's not 1. Okay? So my vertical asymptote is at X equals 1. When I solve that back, subtract 1, X minus 1 equals 0. So that's going to go into my vertical asymptote. And then I just plug in my X and my Y point. My X and my Y point are -1 and 4. If it's not given to you, you look for one that nicely crosses through a cross section. So this one was -1 and 4, nicely crossed through a cross section, so I could use that. I could have used -2 and 3, that nicely crossed through as well. But if they give you a point, use that one. Okay, so this one was given, -1 and 4. So I'm going to go 4 equals A, -1 minus 7, -1 plus 3, over -1 minus 1, -1 plus 3. So I'm going to get 4 equals A times -8 times 2 over -2 times 2. And before I go to solve anything, I'm crossing off these 2's. If I don't, you're going to get zeros, so just cross them off, okay? So we get 4 equals -8A over -2. All right, multiply by -2, get that off. -8 equals -8A, divide by -8, A equals 1. So my equation, I fill in my A value, so I'm going to get 1, X minus 7, X plus 3, over X minus 1, X plus 3, and then I FOIL them together. It's not always going to be 1, guys, so make sure you check it. If you don't check that A value and it's not 1, you're in trouble. So we get X squared minus 7X plus 3X minus 21 over X squared plus 3X outside minus 1X inside minus 3 left. So you're FOILing. So we get X squared minus 4X minus 21 over X squared plus 2X minus 3. Now remember, you can type these into your calculator. You just make sure numerators in brackets, denominators in brackets. It should match the graph. That's the great thing about these. When you're done the question, you should either be super happy because you know you got it right because it matches, or super sad because it does not match and you go back and try again. Okay? That's the end of it. I'm sorry it's a very long lesson, but this is one of the most intense lessons to learn of the year. It takes the longest, so we did one this week. Okay? Have a happy Easter.